hey, do you remember analytic 1? And like how position, velocity, acceleration all. And then I got it wrong the first time. It's like, what am I doing? I was like, there's an initial condition. I need a constant. It was like a 10-point problem that I was super excited that I was like, yeah.
Yeah, I always felt that when you got the big one right, and you got that like big set of points, like good feeling.
And just when like you get something wrong and then you figure out what you were like on the classical final, I think I was like, why did he give us a terminal velocity for this problem? I don't need it. And then I got to like part 3 and I was like, this is where I need terminal velocity. How'd you make those so small?
What did I make so small? Oh, the points?
Because you commented on mine, you're like, that makes your plot so fat. I tried it wouldn't go smaller than what I made. I don't know why.
Okay, I'll show you how I do it.
Because it let me do like 0.25 or something, and then it wouldn't.
If you go to line, no line, marker options, you can do the built-in and make this a lot smaller. That'll make it small. And the other trick is make your plot really big. That's right.
Yeah.
And then just increase the font. What's that? Or do it on Python, and then you can make your.
I thought about doing it in Mathematica, but I was
plots any.
You can make the plots look nice on Python, but that doesn't help if you don't read the directions and are plotting the wrong thing.
That's true.
I don't know how long it's going to take to like because you can like reference an Excel file in it.
Yeah, no, you can. A single line will import an entire Excel file into
how
readable.
long is this going to take to import this?
Oh, Python works a lot faster than Excel does.
Yeah, it's fast.
Yeah. So that's nice.
So there's a few times when I'm like.
Okay, hey everyone, it's time to start class. So Wednesday's exam 1, in class, 50 minutes.
Is the formula sheet for that going to be posted on Canvas?
Yeah, I made that this morning and I was like, oh, I should post this. And then I got distracted with something else and I didn't post it. But it's ready to go. I will post it as soon as I remember after class. Question.
Kappa this week?
There's no Kappa up this week. I'll probably put it up.
That's all I wanted to hear.
I'll probably put it up. Yeah, sometime soon. It will be due sometime next week.
Okay.
Morning, Hunter.
Hola.
Other questions? We're just talking about exam 1.
On a scale of 1 to 10, how much is this exam going to make you cry?
I mean, I think it's easy, but
Comparison to what they.
isn't always I'm not always the best judge of how these exams are.
The person with a PhD in the topic.
Right. So.
Maybe not the best one to say.
Yeah, I think the exam the average will be in the 70s. Ish. Hope it's not lower than that. I don't think it will be. Yeah, I'm still tweaking length stuff. I'm still deciding how much I want to put on it. It's pretty much ready to go, but it might be too long now. I might cut some more stuff out. So we'll see. I'm still tweaking. Okay, excellent. So let's do APOD first, because if I don't do it first, I will forget. Today's astronomy picture of the day. Bam! Look at that. It's a comet. This is Comet Neowise. Last summer, this is a pretty good in fact, this is the first comet that I had seen naked eye since the late 90s when Hyakutake came. Did anybody else see this comet? This one? Yeah, this was a naked eye visible comet in the northern hemisphere. It was a pretty good comet. You couldn't see any of this detail, obviously, just naked eye. But look at all that detail. Right? If you ever wanted to know what a comet was or how it worked, today's astronomy picture of the day is your one-stop shopping guide, because all this stuff is labeled with explanations on where it comes from and why it's like that. You can't read that because it's so dark in here. So dark. There we go. How about that?
Complete conspiracy. Without fail, every time I remembered to look up for the entire month it was visible, every time I was like, oh shit, is it still visible today? I'd go up, I'd look it up, yes, it's still visible, go outside, it's like overcast out. And the clear it is, I guess I just couldn't look up for my homework.
That's sad. Yeah. It was. Oh, nice. Nice. Yeah, we even went down here on Nations Road, and we were looking due west, and it was pretty good. If you were in a spot just on the valley, you were good enough that you could see it pretty well. Anyway, if you want to know how comets work, here's your 2-minute lesson. Most people think that, guess the direction that this comet's moving in. Pop quiz.
Towards the sun.
Down, right, that's what everybody says. This comet's actually moving to the left on the screen as we move. So the sun is down, and it's the solar wind that's actually, so comets are kind of dirty, fuzzy snowballs. As they get close to the sun, they heat up, and their ices melt, and trapped gases get released. And those trapped gases interact with the stellar wind. There's a wind pushing away from the sun, and that wind is what is causing this tail to develop. So here is the actual motion of the comet. Here is the direction of the solar wind. And the stuff that gets emitted by the comet is different masses, right? This is the ion tail. Ions are blown back a lot more by the solar wind because, one, they're charged, and the other charged particles exert more force on them, and two, they're lighter, and so they experience more acceleration, even by the same force. This is the dust tail. The dust tail is heavier stuff, and it is accelerated obviously less, and so you get it trailing off in the anti the direction of motion, but it's still being pushed away from the sun primarily. So why is it red? That's sodium. Why is it blue? That's the ions. White dust tails. They get a little green coma here from diatomic carbon. Who knew? I didn't even know that. So there you go. The anatomy of a comet and how they work. You can amaze your friends with your cometary knowledge. Uh-oh, somebody chatted me. Ah, right. Tyler asked, is a calculator needed? A calculator, yes. You will need a calculator. I'd say half of the test is writing description stuff, and half of the test is doing calculations of some kind. So no Mathematica, you shouldn't need Mathematica, but you will need a calculator. Okay, so I wanted to close the loop on this homework problem that you handed in last week. The Gaia data. This is harder than you might think to plot big data sets. The data set that I gave you was more problematic than I thought it was because there were not lots. I mean, it was a huge data set, but many of the rows had data missing in certain columns. So you had to filter those out in some way and figure out how to do that. And then once you did that, you could make these two plots, one of which was all of the stars out to 25 parsecs, which looked like this. And the other one was all of the stars whose apparent magnitude is brighter than 6. And that's what this one looks like. So one of these, this is a major, so these are completely different plots, right? It doesn't even really look like they're the same thing. We are plotting the same thing. And in fact, I've even lined this up and scaled it so that the scale here is exactly the same in both these directions. This one shifted over, obviously, so you can see both of them. But you can, these are exactly the same. These are points are a little bit bigger, but you could move these over, exactly over, and they would line up there. So what do you see is the difference between these two and why? Let's just have a 2-minute conversation about this. What do you think? Yes, right? So these kind of peter out at absolute magnitude 8 or so, and really there isn't much below 6, much fainter than 6. And there isn't much here brighter than 6, right? These are huge amounts of stars down here. By the way, this is probably fake stuff down here. At the faint end of any survey will be fake objects. And so you're seeing, I think that's what you're seeing down here is objects that are at the faint, that are probably not even real objects because there shouldn't really be anything here. This is sort of the bottom of the main sequence. And this is you're seeing. So obviously, right. One of them is insisting that these stars are bright, although appear bright and not are intrinsically bright. It still self-selects for the most luminous objects in the galaxy, which makes sense, right? This is one of the problems with doing astronomy. When you do a survey, what's the easiest thing to do? Well, my telescope is sensitive to magnitude 18, so I'm just going to take everything out to magnitude 18. That does not anywhere near give you an accurate census of what is out there. You really need a volume limited sample, which is you go out and you select everything out to a specific volume. This gives you the true distribution of stuff in the universe, assuming we've measured it all down to a certain point. This does not give you a real sense of what the true distribution of stuff in the universe is. You can see this stuff at the top of the main sequence, these guys up here are very rare. There's very few of these, there's even very few giants, right? But if you look at the brightest stars in the sky, that's where all of these things are. There's all these hot, bright blue stars up here, plus all these really bright red giants, because those are the most luminous stars in the galaxy. And we can see them at vast distances. Even though there aren't that many of them, they're outshining by a lot everything that's going on down here, by a lot. So this is actually a useful exercise to see what real HR diagrams look like, but it's also useful exercise in understanding the importance of surveys and what it means to be a magnitude limited survey, meaning a brightness limited survey, versus a volume limited survey. These are much more important surveys, but they're much harder to do if you want a real census of what everything that's out there is. Because think about this, I mean, I don't know, there were 5,000 or so of these within 25 parsecs or so. This is a catalog of 1.6 billion stars, right? I gave you already a hugely cut down version, 1.6 billion with a B, right? It's a crazy catalog, right? But if you just take those 1.6 billion, you're going to get a picture that looks like this, because the whole thing is a magnitude limited sample. You have to take a much restricted view of your full sample if you want to just do a volume limited sample. Okay, that's my soapbox speech about surveys in any discipline, but astronomy especially. You have to be careful about this.
Is that little echo on the bottom left?
This?
Is that like similar to what you were saying about the other tuft at the bottom right?
No. This is not real. This is real. This is the white dwarf sequence. We haven't talked about what white dwarfs are in this class yet. But these are the corpses of sun-like stars and similar mass stars. And you can see why they're dwarfs, right? We move up and to the right, we're getting bigger in the HR diagram. We move down to the left, we're moving to smaller things. These are tiny. These are sun-like masses with Earth-like diameter things. And very faint. You know, the sun's up here somewhere. The sun's up here somewhere, right? That's the other thing. This thing extends huge amounts way past where the sun is. So that's also fun. Okay. We were talking about, and we left off, how to measure the abundances of the composition of stars, how to measure the compositions of stars, how to express that in numerical terms. We talked about X, Y, and Z, capitals, these are the mass fractions of hydrogen, helium, and metals. And I made the crazy claim that metals is in fact anything that's on that table above hydrogen, helium, 200. Right, and we even wrote down these numbers down with the sun. But there's other ways. This is just one way, and it's not even a very typical way to do it for stars. This is one of the ones where there isn't really a consensus, and different disciplines, like solar physicists, will almost always use these. Stellar physicists, stellar astrophysicists will use other things for other elements and things. So, especially if you want to know how much iron is in your star, Z doesn't do it, right? You need to actually break it down further than that. So, other ways to express abundances. All right. Let's see. So, right. So, we usually use log scales because often we're comparing the amount of iron in a star to the amount of hydrogen in a star. And those are many, many orders of magnitude apart. And so it's easier, because these numbers are so vast, to work on log scale. So this is typical way it's done. So for instance, when we're talking about abundance of lithium, and I do a lot of abundances of lithium, we'll express it this. A just meaning abundance, and then whatever element you want. And this is typically defined to be 12 plus the log base 10, we're in the log base 10s, of NLI over NH. So let's break this down. These are the number, this is actually the number of that element in the atmosphere of that star, right? This is obviously not a number we want to calculate, but this ratio is something that we can handle. How much lithium is there in a star relative to hydrogen? Now this is obviously going to be a very small number, right? 10 to the minus 9, 10 to the minus 10, 10 to the minus 11. So when we take the log 10 of it, we're getting a number here that's negative 9, negative 10, negative 11. Now, those numbers are, fine, but who wants to deal with negative numbers? So what do? Oh, let's just add a constant to it. Why 12? No real reason, but it makes those numbers kind of positive and small. It's arbitrary. But it makes it so that, our abundances that we're getting are usually between 1 and 3 for lithium. So those are nice numbers to deal with. But that, and if you're comparing one lithium to another, you don't really care about this 12, you don't really care about this. You're just comparing the lithiums really of those two stars. It doesn't matter what your scale is. You just know it's a log difference between them.
So is that only for lithium?
No, you can do a oxygen or
12, right?
it's still going to be 12 for pretty much. This is again, I'm not sure. In every paper I've ever written has this as a little footnote when we say elite, and I think this is pretty standard now. I've never seen it anywhere else, but you could define B lithium to be this plus 8 or something, but that would be why? Because 12, so lower limit of what's possible. Internet connection apparently is unstable. Okay, and it.
Except for hydrogen, small. So I think
yeah, but then the on that star that gets confused, right?
Right?
True. Hey, you're back. Okay, I'm going to share again. Okay, so here is an actual plot for my dissertation, and there it is, A lithium. And look at these numbers from 0 to 3. Now, this is a log scale, right? So these stars are 10 times more lithium in them than these do, which have 10 times more lithium. This is a huge range in lithium abundances. But this is, again, 10 to the minus 9 of the hydrogen abundances of these stars. This is really how this scale works. Right, and this is if you, this is not my plot. I would never have done this, but you can see if you don't use A-Lee, you get plots that look like this, right? This is the number of this is the thing that's in this thing here, right? But they haven't normalized it to anything, and it's just 10 to the minus 10. So this would be 2 on the other plot, and this would be 1, and this would be 0. It's the same plot, but it's kind of nicer to see 0, 1, 2, 3 than it is 10 to the negative 12 than the negative 11. I don't know. It's just easier to work with. Okay, another one. Often you will hear people say the metallicity of a star. What do they usually mean? They're almost always talking about, let's go back to iron. Let's go back to the periodic table. Something called Fe on H. And what is that? So there's a square bracket, Fe/H, and this is usually how this parameter is written. And this is defined to be log base 10 again of the number of iron atoms in the star divided by the number of hydrogen atoms in the star of the star minus the log 10 of that same ratio for the sun. So this is a very convenient, well, let's, so this is, again, a thing that's normalized to the sun, which makes it very useful, right? So you can measure the amount of iron in the sun relative to hydrogen and take the log of it, and you're going to get a number that's like 10 to the negative 10 or something. This is going to be a negative 10 or something. But if a star has exactly the same amount of iron relative to hydrogen as the sun does, this is going to be 0. And so this is a scale that is normalized to the sun. It's a log scale in abundance that is normalized to the sun. So, for instance, if it's 0, it is equal to the sun. If it's positive, it's more than the sun, or metal rich. If it's negative, it has less iron than the sun, and it's metal poor. Now, we should call this ironicity, right, and not metallicity, because we're really just talking about iron here. Iron is, though, a good proxy for the metals in a sun, in a star. If you increase the number of iron atoms in the sun in a star, you're typically, and by similar orders, increasing all the other elements in that sun, in that star also. So, yeah.
Isn't iron like also the last fusion product?
It is. It is. We'll get to that in a bit. But this is also the last. This is the most stable element that there is, and therefore the last element that you can fuse in fusion to get energy out.
Oh yeah, because it's not going to get anything else. Okay, cool. Yeah.
That's right. But that's not really why it's here and used as a proxy. It's, well, that is part of it because there's a lot of it. But the other reason is that there are iron lines everywhere. If you take a spectrum of a star anywhere in the visible part and probably anywhere in the infrared part too, there's just hundreds of iron lines there to measure. It's just easy to measure. it's much more an empirical, easy to measure thing than it is anything else, really. So, right.
So is that how you would actually like measure these ratios, like looking at the iron lines compared to hydrogen lines?
No. I mean, these numbers are so small that you basically assume that these are trace amounts in a sea of just hydrogen itself, right? So, yeah. So physically, how it's done? Well, you need a model atmosphere, and you need that model atmosphere to how you're actually doing this is you have an absorption line, and you're measuring the strength of that absorption line. And the more iron there is in that star, the more the stronger that line will be. Now, doubling the amount of iron in the star is not going to appreciably affect the amount of hydrogen in the star at all, right? So you're really just measuring the amount of that, the total number of atoms in that column density, and assuming the rest of it's pretty much hydrogen.
Is this something that kind of like trends with similar stars, like you all red giants have like a similar amount of iron in them, or is it
right?
Could they have the same as?
Yeah, that's a great question. Why do stars have different iron abundances? It's not that all red giants have. In fact, since iron's the last element to be fused, it's trapped at the center, right? That's where you're fusing the element. You're not seeing the fusion product of the surface of the star. What do you see at the surface of the star? You're seeing basically the stuff that it was born with, right? And so you're seeing how much chemical evolution has occurred in the galaxy before that star formed in the surface of that star, and not how much evolution that particular star has gone through. So the first generation of stars probably had 0 iron. We've never seen one of those stars. We don't think they're any existing now. They were probably so massive that they went supernova almost immediately. The next generations of stars that got chemically enriched the interstellar medium, the next generation of stars had more heavy elements. The next generation had more. The next generation had more. So it's almost, not quite, a measure of age, right? The more metals a star has, the younger it kind of has to be. Although different regimes, the center of the galaxy had this happen way faster than the outside of this galaxy. So you can't really just point to this and say that star's that age, because it depends on where it was when it was formed, and it may not be anywhere close to where it was formed anymore. So that's even a tricky guessing game. Yeah, but this is basically a proxy for, certainly if you go to very, very metal poor stars, and we have seen some very, very metal poor stars, like F(H) of -5, of -7, right? That's a log scale. That's -7 is 10 million times less iron compared to the sun, right? These are some of the first generations of stars, had to be, that formed in the galaxy. And those are cool stars and interesting stars to study because they hopefully have preserved some other things about the conditions of what the universe was like in the very beginning. So, high metallicity stars, they could be any age, really. Low metallicity stars, though, sort of have to point back to very early times.
So their metallicity. So it sounds like you're saying that the fusion process within the star itself doesn't have a strong contribution to its own metallicity.
That's right, because it's all trapped in the center.
Okay.
Those fusion products don't reach the surface, and you're only observing the surface of the star. It's much more a function of the composition of the nebula that it formed out of.
So then that must mean that, like you were saying, it would be a fairly reliable tell for their age, regardless of their size then.
That's right.
So that must mean like massive main sequence stars must tend to have higher metallicity because any of those that are still around would have to be formed.
Yeah, you see 0 high mass main sequence low metallicity stars. There just aren't any of them. we'll talk about stellar populations in the galaxy later on and have this conversation in more detail. But that's one of the reasons why this is an important number. By the way, if you've ever seen my superhero character out there, his battle cry is FE on H, because we do measure a lot of them in the work sometimes that we do. Okay, and this can work with any element. So you want to know OH. This is the amount of oxygen in a star relative to hydrogen normalized to the sun. That's sort of what these square brackets mean. It's normalized to the sun. It doesn't even have to be iron, hydrogen. Really. I've seen Fe over O, for instance. How much, if you want to know, these are general metallicity things, but this is, now, how does iron scaling to oxygen compared to this thing, right? If all these elements are scaling with each other directly, then this will be 0. But if oxygen or iron is increased more, this gives you a handle on how those different abundances are playing out in the various stars that you're talking about. Okay, so that's an aside on how astronomers measure and report abundances of elements. Let's go back to the big picture and think about where we were, which was we had written down 2 stellar structure equations, which was exciting, and we had even written down an equation for the gas pressure, according to astronomers. Are there other sources of pressure? So we have gas pressure already. Are there other sources of pressure?
Yeah.
Well, I wouldn't be asking if the answer was no. It would be a dumb thing.
It'd be pretty good, actually. But no.
There's a good rhetorical method. So what's another form of pressure?
Magnetism?
Yes. Magnetic fields can hold things up if they're strong enough. We're not going to be considering magnetic fields because, well, this is actually a good time to step back and talk about what we are doing. We're developing this 4 stellar structure equations, which represent kind of the standard model of stellar evolution. The standard model of stellar evolution does not include complicating effects like magnetic fields and rotation. Why? They're hard. And 2, they make it so that anytime you have something that's dipolar like that, they turn it from a 1-dimensional problem into a 2-dimensional problem at least. And that makes the problem infinitely more complex. So we're going to be ignoring magnetic fields, even though they probably play an important role, at least at the surface of the sun, and certainly for some stars are extremely important. And we're going to be ignoring rotation, even though for some stars that becomes important. But we're going to be building our basic star. And then we can think about, if we want to, well, how does spinning this star up change things? How does adding a magnetic field to the star change? So we won't do that much of that, but you can once you have the basics in place. So that's a good guess. Radiation pressure. There's a lot of radiation coming out of these things. Surely it makes a difference. And sometimes the answer is yes. So you might remember, I think we even wrote an equation like this in Analog 3, but it probably wouldn't look exactly like this. I'm not going to derive it. If you want to see it derived, you can look in the book. Radiation pressure is 4 sigma over 3c times t to the 4th. Which shouldn't be surprising to see sigmas and t to the 4th in there, because that's the energy given off by a black body radiator, sigma t to the 4th. That's p over a, actually, sigma t to the 4th. So you got some other constants in here to turn that into a pressure instead of power.
You said this is pressure over area.
This is pressure. Sorry, this is force over area. right? But if you remember the, what is it, the Boltzmann law? P over A, that's power over A equals equals sigma T to the fourth. So this is similar. We've got a power now, we've got a C here to change the units from power to pressure, basically. So the total pressure, of course, then is, there may be others too, but these are all we're going to think about. P gas plus P rad. So you can just add these things, they just add up. Rho KT over mu mh, which is our gas pressure formula, the ideal gas law, plus 4 sigma over 3c times P to the fourth. Now, for the sun, P gas is greater than P rad. So, this is the more important term in that equation. But there are astrophysical instances where the radiation pressure is not only bigger than the gas pressure, it's much bigger than the gas pressure. And so you can't ignore it in all situations.
Is this radiation pressure like a general, I mean, so off the top of my head, I'm thinking about how different wavelengths of light interact with different parts, can pass right over particles depending on their size. So does this adequately account for that?
Yeah, that's a good question. Meaning,
Like the energy should only be imparted at each wavelength of
because a hydrogen atom can only absorb wavelengths, photons of a specific wavelength.
Yeah,
Because of the energy levels
Does
involved.
it all just add up nicely for this, or?
Well, I mean, this is thinking about a soup that's hot enough that most of the particles are ionized and therefore have charge. And the nice thing about charged particles is they can emit and absorb at any wavelength. It's just any acceleration of any charged particle will produce a photon, and any charged particle can absorb any photon to change its acceleration, to accelerate it a little bit, right? So the thing we've been talking about in terms of are for non-completely ionized things, but why is it that this even works, right? If you have a hot, why is the Planck function even there and not specific wavelengths? It's because the hot objects are emitting at all wavelengths because they're really just jiggling charges, right? So this is the same kind of argument. That if you have a dense, this is the hot dense gas as opposed to a thin cool cloud of gas, right? You get this, and in the interior of a star, you get this also, and everything's bouncing around and absorbing photons and in a way that is very Planckian, and that gives you this. Does that make sense?
Yeah.
All right, let's talk about energy sources. Where are stars generating their energy and how? So the energy output is huge. The luminosity of the sun is 3.8 times 10 to the 26 watts. The sun is a 4 times 10 to the 26 watt light bulb. That's a lot of watts. Where does it come from? How long can it last? We know the answer today, but 120 years ago, we actually did not know the answer to this question. And so let's rewind the clock, pretend it's 1900, and we're trying to understand how the sun works and generates energy. We know it's nuclear fusion today. We didn't know what nuclei were in 1900, much less what fusion was and how it could power anything and give us any energy out. So this is actually a conundrum because people were finding rocks on Earth that were billions of years old. And we didn't really have a way to power the sun for very long. But what was the state of the art in 1900? What was the best way to power the sun that they knew of? It turns out that it was gravitational potential energy. If you take something that's very large and shrink it a little bit, that gravitational potential energy is released, and it can go into heating a star and energizing a star and radiating lots of energy. That can't go on forever, obviously. As you'll keep getting as you generate that energy, you keep getting smaller and smaller. But the sun has a lot of mass, and it is pretty big. So there's a lot of energy actually stored just in the gravitational potential energy of the sun itself. So let's go ahead and kind of a fun exercise to figure out how much energy that is. How much gravitational potential energy does the sun have? So to remind you, the gravitational potential energy between two particles separated by r we usually call this U, and it's negative g times the mass of the first particle times the mass of the second particle divided by r. Why the negative sign? Do you remember?
This is a well you have to overcome.
Yeah, basically we define zero energy to be having these two infinitely far apart. And the gravitational potential energy decreases as you bring them closer, and it increases as you take them further apart. This is a nice 0 point. You can sort of define your 0 point anywhere, but this is a convenient 0 point to make it zero at infinity, so that everything gets smaller as you move in and more negative. So you can think about the gravitational potential going up, even though it's going down, in this negative sense. It's a little confusing. The negative sign sometimes throws people off. So as the distance decreases, the potential energy goes down because the negative sign. So this goes up. As this gets smaller. This quantity gets larger, but U goes down because of the negative sign. Okay. Now, this is two particles. Obviously, if we're going to do this for the sun, we need to account for every single particle in the sun. Obviously, we don't want to integrate over all of them. Well, we don't want to numerically integrate over all of them. We can hopefully do some sort of mathematical integration, which will be easier. So, need to account for every particle in the sun. So let's draw our spherical symmetry thing again. That's a pretty Easter egg looking thing, sorry. And here is a shell. So again, let's consider, and this is obviously just a shell, and what's a very much larger star. Let's consider the shell of radius r from the center and thickness dr. And like before, let's say mr is the total amount of mass that's contained inside of the shell of radius r. Right. Again, we can make the very cool assumption that the gravitational potential energy on this particular particle inside that shell can ignore everything outside of that shell and only assume and only consider all the stuff that's inside the shell. And not only that, this is equivalent to all the mass being at the center because of symmetry, because of the radial symmetry. Makes our life much, much simpler if that's the case. So we can ignore the mass outside the shell and assume all the mass interior is at the center. So du across this shell is negative g times m of r times dmi. Why have I written dmi there? Oh, yeah, I guess this is just the shell, the ith shell over r. So I guess this is the, right. So dm, this is the ice shell, is going to be, we wrote this down before. It's the surface area of that shell, which is 4 pi r squared, times the density times the thickness, dr. That is the mass contained inside, within the shell. This is the mass inside the shell. This is the mass within the shell. So this is the total potential energy of the whole shell itself. So you can plug this all in. U is negative G times m of r. Plug this in for dm. You get 4 pi r squared rho over r. Some r's cancel out. That's nice. This becomes negative G times mr times 4 pi r rho dr. Now, we could just integrate this, except that m of r is varying with r and rho is varying with r as well. Right? These are not constants. These are changing as you go out. So we're going to have to find some functional form or assume something for these guys before we go any further. Let's make an approximation. What am I doing on time? I got 4 minutes. Let's make the approximation that the sun has constant density. That is a patently wrong thing to do, but we're just doing the order of magnitude calculation anyway, so why not just make that? It's going to make our lives easier, and we're not going to be off by a ridiculous amount. So let's approximate rho equals constant, and let's just set that constant equal to the average density of the sun. It's a reasonable thing to do. This is going to be the total mass of the sun divided by 4/3 times pi r cubed. Again, the capital R and the capital M says this is integrated out to the surface. This is the total radius of the sun and the outer mass, the total mass of the sun. And of course, 4/3 pi r cubed is the volume of the whole thing. We also know m of r then works well. M of r is just 4/3 pi r cubed times rho bar, right? So wherever we are, m of r is just the volume contained inside that shell times the average density. So, right. du, therefore, is, I'll give this a single approximation because we have made a whole bunch of stuff that, that doesn't even deserve 2 squiggles, just a single squiggle. So we've got negative 4 pi g rho bar g rho bar, that's that. Those are all constant. We've got our m of r, which is 4/3 pi rho bar. And we've got an r to the 4th now, dr. There's 1 comes from here and 3 of them come from there. We can integrate both sides. These are all constants except for the r4 to the 4th dr now. And integrate, this is u roughly equal to negative 16 pi squared g over 3 times rho bar squared. This gets crazy fast. And you get this thing, which is r to the 5th over 5. This is roughly negative 16 pi squared g over 15 times r to the 5th. Right, we're integrating from 0 to the outer radius, which is why this little r becomes a big R. I should put that explicitly, 0 to capital R. Integrating over the whole star. Oh, right. And then this rho bar squared, the only thing I don't have is the rho bar squared, but we know what rho bar squared is. We can plug this back in here. Rho bar squared is 9m squared over 16 pi squared r to the 6th. And this whole thing, actually, r's cancel out, pi's cancel out, 16s cancel out, actually becomes pretty nice. I'll write it over here. UG is approximately negative 3g capital M squared over 5r. Making the assumption that the sun's density is constant. Okay, we'll plug some numbers in and see what we get for a potential energy, and then see how long, given the sun's present luminosity, it could last, given its available potential energy and how fast it's using it. Spoiler alert, it's not 4 billion years.
Does this contribute to the luminosity like a little bit? Is it shrunk?
It doesn't now, because the sun is stable and the source of energy at the center is holding it up and preventing it from shrinking. But it did. There was a time in its life when the sun, this was the dominant source of energy generation in the sun, when it was still a baby star and hadn't started fusion in the center yet. It was slowly contracting and slowly getting smaller and slowly heating up, and that gravitational potential energy was turning into thermal energy and slowly heating the core of the sun up until it was hot enough that it could actually fuse hydrogen and helium, and at that point the contraction stops because there's a stable source of energy. Good question. Okay, done for today. See you on Wednesday for exam 1. And somebody is on astrobites this week still. Who is that somebody?
I think me, right?
Oh, we actually mentioned this last time, didn't we?
Yeah.
Yes, it is you. So sometime Wednesday, I would like an article. But it can be after the exam if you want.
Sounds good.